Hello everyone, my name is Sajid Muslihi. In this video, I'm going to talk about the energy conservation equation or the energy equation, which I also talked about in the previous video. But here, I'm going to change the equation a little bit and manipulate it a bit to make the code faster. So, how am I going to do that? I'm going to replace the internal energy, the specific internal energy in the accumulation term with what it is equal to. We know that specific internal energy is equal to specific enthalpy minus pressure over density. So instead of using the internal energy and calculating it again and again, we directly use specific enthalpy minus P over rho. And this helps us speed up the program. So let me show you how it works. This is exactly the script that I talked about in the previous video. The only change that I'm going to make is the energy conservation equation, as I said. Now this is the energy conservation equation. As I said before, this is the energy accumulation term. This is the energy advection term, and this is the energy conduction term or diffusion term. So we know that for the calculation of the accumulation term, we use internal energy, right? This is the internal energy of the fluid, which is guessed, and this is the internal energy of the fluid in the previous time step. This is the current time step, which is just a guess. This is for the previous time step. So as you see, we calculate these internal energies, specific internal energies, again and again in each iteration. So instead of doing that, we use this formula directly. We know that fluid specific internal energy is equal to fluid specific enthalpy minus pressure over density, right? So instead of using actually this relation again and again in each iteration, we remove this completely. We remove it completely, and we come here, and what we do is we also remove this line because we no longer want to calculate internal energies again and again. And when I say internal energy, precisely speaking, specific internal energy, I'm talking about fluid specific internal energy because we also have rock internal energy, which is calculated actually with another formula. And I'm not going to make any changes there. I'm just going to make changes to the fluid specific internal energy. So I removed fluid specific internal energy here. So let's replace it with what it is equal to. As I said, it is equal to enthalpy H F underline underscore automatic differentiation minus pressure over density. Great. So this is what it is equal to. Let's also do it here for the previous time step. For the previous time step, let's just copy this and paste it there. And do this to make sure that they're all in the previous time step. All right, so now this is what I was going to do, but we know that if we multiply this by these coefficients, this will be removed. Rho F, this will be removed. So I could say that I can remove this here, and also this one, and also rho times PV underscore AD, and this is actually the simplified form of what we just had. So yeah, this is good, and we can also simplify this one. We know that this is actually, this will be multiplied by this, and this is in the denominator, in this is in the numerator, and so it will be removed. So in order to simplify that, we do this, and we put this here. Great. And actually, let me see if everything is correct. So right, so let me put the current time step in parentheses, and also the previous time step in parentheses. So minus this, and also this must be actually positive. All right, so yeah, this is what we needed to do, and this is actually the simplified form of what I just wrote. So yeah, that's it. And with what we just did, we no longer need to calculate internal energy again and again, and we just use enthalpy. We just use enthalpy to do that. Of course, as you see, we also need to calculate enthalpy in the previous time step. So let's do that here. HF0 All right. So yeah, that's it. And now, instead of calculating 3 parameters, in the past we calculated 3 parameters, right? Enthalpy at the current time step, internal energy at the previous and at the current time step. So 3 parameters. Now we only need to calculate 2 parameters: enthalpy at the current and at the previous time step. So this increases the speed of the program a little bit. So yeah, let's run the program to see if it works without any problems. Because the video recorder is running, actually the laptop has become a little bit slow. So let's wait. Yeah, let's stop. Let me stop the actually video recorder, and after it starts, I will show you the output. All right, as you see, it says that it requires a dot here, so I forgot to put a dot over here to do element-wise multiplication. So let's run it again. All right, and this is the solution to last time step of the simulation. All right, so this is actually what I was going to talk about, how we can manipulate the energy conservation equation to make it simpler, which leads to actually speeding up the program. So thank you so much, everybody, for watching this video, and hope you're having a great time.